Hello, and welcome to Space for Sleep. Far beyond the orbit of Earth, beneath the pale light of a distant sun, there is a world where rain falls from orange clouds. The rain is not water. At the temperature of this world, water ice behaves more like stone than snow. The droplets are methane, chilled until the gas becomes liquid. They fall through a dense nitrogen atmosphere, darken the ground, gather in channels, and flow toward lakes and seas. Some rivers wind through broad valleys. Some branch into smaller tributaries. Some disappear into porous terrain. Near the poles, dark seas spread across areas comparable to large countries on Earth. Along the equator, dunes rise in long parallel lines and continue for hundreds of kilometers. Their grains are not ordinary sand. They are made largely from organic material produced in the atmosphere and slowly carried down to the surface. This is Titan, the largest moon of Saturn. Titan is larger in diameter than Mercury, though much less massive. It is wrapped in an atmosphere thicker than Earth's at the surface. It has clouds, winds, seasons, erosion, shorelines, drainage networks, dunes, mountains, plains, and stable bodies of liquid exposed to the sky. The details are profoundly alien, yet the broad patterns are familiar. On Earth, sunlight moves water through evaporation, condensation, clouds, rain, rivers, and oceans. On Titan, a weaker sun helps move methane through a similar cycle. On Earth, silicate rock forms mountains and sand. On Titan, water ice forms much of the solid ground, while carbon-rich particles form many of the dunes. On Earth, water is the ordinary liquid of the surface. On Titan, water is part of the bedrock, and hydrocarbons take its place in the weather. No other known moon possesses such a dense atmosphere. No other world beyond Earth is known to maintain stable lakes and seas openly on its surface. Titan is not an imitation of Earth, and it should not be described as a frozen Earth in any simple sense. It is a separate planetary experiment, governed by the same physical laws, but using different materials under different conditions. Its atmosphere contains mostly nitrogen, with methane and smaller amounts of many other gases. Sunlight and energetic particles break those gases apart. The fragments recombine into increasingly complex carbon-bearing molecules. Some remain as gases. Some condense into haze particles. Some settle downward and coat the ground. The chemistry has continued for immense spans of time. Titan therefore offers several kinds of history at once. Its rivers and shorelines record climate. Its craters record impacts. Its dunes record winds. Its atmosphere records chemical reactions. For more than a decade, Cassini measurements were widely interpreted as evidence for a global ocean of liquid water beneath the ice. A major reanalysis published in late 2025 challenged that picture, suggesting instead a deep hydrosphere dominated by warm, slowly deforming high-pressure ice, slush, and scattered pockets of liquid water. Titan's interior is now one of its most active scientific debates. Its surface, meanwhile, preserves organic material that can help reveal how chemistry advances toward greater complexity before biology begins. There is no evidence that Titan is inhabited. The surface is extremely cold, the available energy is limited, and liquid methane is a very different solvent from liquid water. Yet Titan remains important to astrobiology precisely because it allows the boundary between ordinary chemistry and prebiotic chemistry to be studied in an environment unlike any laboratory on Earth. A future spacecraft named Dragonfly is being built to explore that boundary. It is a nuclear-powered rotorcraft, roughly the size of a small car, designed to fly through Titan's thick air and land at many locations. Its launch is planned for no earlier than July 2028, with arrival in late 2034. It will not be a mission that simply searches for living organisms. Its central task is to study Titan's chemistry, geology, atmosphere, and habitability, especially in places where organic material may once have mixed with liquid water. Before following that future journey, we can begin with the much older human journey toward understanding Titan. For most of history, Saturn itself was the farthest planet known. To unaided eyes, Saturn appears as a small golden point that moves slowly among the stars. Its rings are invisible without magnification. Its moons are much fainter still. The invention of the telescope transformed Saturn from a point into a system, but the transformation took time. Early telescopes produced confusing views of the rings, which could resemble handles, companions, or changing extensions on either side of the planet. The Dutch astronomer Cassini-Huygens improved the design and manufacture of telescope lenses. On March 25, 1655, while observing Saturn with an instrument he had built with his brother Constantine, he detected a small point of light near the planet. Over repeated observations, the point changed position in a regular way. Huygens correctly concluded that it was a moon orbiting Saturn. He did not call it Titan. For many years, it was simply Saturn's moon, and later Saturn's sixth satellite after additional moons were discovered and numbering systems changed. The name Titan became widely established in the 19th century, following a suggestion by John Herschel to name Saturn's moons after the Titans and related figures of Greek mythology. Huygens also helped explain Saturn's rings. He proposed that the planet was surrounded by a thin, flat ring that did not touch it. The same scientist therefore contributed to revealing both the ring system and the largest moon moving beyond it. Titan completes one orbit around Saturn in a little less than 16 Earth days. Huygens estimated that period with impressive accuracy, but a period and a faint point of light were almost everything astronomers could know for centuries. Titan's size was difficult to measure. Its surface could not be seen. Even the existence of its atmosphere remained uncertain until the 20th century. A decisive change came in 1944 when Gerard Kuiper observed Titan with a large telescope at McDonald Observatory in Texas. He examined its infrared spectrum and found absorption caused by methane. A moon too small to retain any meaningful gas would not produce such a signal. Titan must possess an atmosphere. This was the first confirmed substantial atmosphere around a moon. Methane alone did not reveal how dense the atmosphere was, what else it contained, or what lay beneath it. Estimates ranged widely. Some imagined a global ocean of hydrocarbons. Others expected a frozen surface covered by organic deposits. The orange color of Titan suggested haze, but the thickness and complexity of that haze were unknown. The first spacecraft encounters provided only partial answers. Pioneer 11 passed through the Saturn system in 1979 and returned measurements from a distance. Voyager 1 then made a close Titan flyby in November 1980. Mission planners had deliberately shaped Voyager 1's path to study the moon, even though doing so prevented the spacecraft from continuing onward to Uranus and Neptune. The choice was scientifically valuable. As Voyager's radio signal passed through Titan's atmosphere on its way to Earth, the gas bent, delayed, and weakened the transmission. From those changes, scientists reconstructed atmospheric pressure and temperature. Titan's surface pressure was found to be about 1.5 times the pressure at sea level on Earth. Pressure, however, is only part of what determines how an atmosphere feels. Titan's air is much colder than Earth's, and therefore much denser near the ground. A person standing there in an impossible protective suit would experience an atmosphere several times denser than terrestrial air at sea level, even though the pressure is only about 50% greater. Voyager also showed that nitrogen dominates the atmosphere. Its cameras revealed almost nothing of the ground. Titan appeared as a smooth orange sphere surrounded by layers of haze. At visible wavelengths, the atmosphere was effectively a curtain. Light could enter and scatter, but ordinary cameras could not obtain a clear view of the landscape below. The failure to see the surface became one of Titan's greatest attractions. The haze was not empty concealment. It was evidence of active chemistry. Methane and nitrogen were being transformed high in the atmosphere into products complex enough to create a planet-wide veil. Beneath that veil there might be rivers, plains, lakes, or something no one had imagined. To reveal it, a mission would need several ways of seeing. Radar could send radio waves through the haze and measure echoes from the ground. Infrared instruments could use wavelengths where the atmosphere is partly transparent. A probe could descend directly through the air and photograph the surface from below the main haze. Cassini-Huygens was designed to do all three. The mission was an international collaboration led by NASA, the European Space Agency, and the Italian Space Agency. The Cassini orbiter would study Saturn, its rings, its magnetic environment, and its moons. The Huygens probe would separate from Cassini and enter Titan's atmosphere. Cassini launched in October 1997. Its route included gravity assists from Venus, Earth, and Jupiter before the spacecraft finally reached Saturn in July 2004. The journey lasted nearly 7 years. Huygens remained attached to Cassini until December 2004. It was then released onto a separate course. For about 3 weeks, it traveled alone toward Titan, carrying batteries, parachutes, atmospheric instruments, cameras, and a radio system designed to transmit data upward to Cassini during the descent. On January 14, 2005, Huygens entered Titan's upper atmosphere. The probe struck the air at several kilometers per second. A heat shield absorbed the energy of entry. After deceleration, parachutes opened, the shield fell away, and instruments began sampling the atmosphere. The descent lasted about 2 hours and 27 minutes. Huygens measured temperatures, pressure, winds, electrical properties, gases, and haze. It listened for sounds. It examined sunlight passing through the atmosphere. Its cameras looked outward and downward. At first, the view remained indistinct. Then the haze thinned enough for the surface to emerge. Dark lowlands appeared beside brighter uplands. Channels branched across the bright terrain and ran downhill. Their shapes resembled terrestrial drainage networks because flowing liquid follows the same basic rules under different skies. Small channels joined larger ones. Valleys curved around obstacles. Material appeared to have been carried from high ground toward a darker plane. The images did not show rain falling at that moment. They showed the work rain had done. Huygens landed in a low region now known as Adiri, near the boundary with the dark equatorial terrain called Shangri-La. The landing was neither a hard crash nor a gentle settling onto deep liquid. The probe struck a damp, yielding surface, bounced, slid, and came to rest. Around it lay rounded objects several centimeters across. They looked like stones, but at Titan's temperature, they were probably made mainly of water ice. Their rounded shapes suggested transport and abrasion in flowing liquid. A dark deposit coated parts of the ground. The surface temperature was about 94 Kelvin, close to minus 179 degrees Celsius. Sunlight was dim. Methane humidity increased near the ground. The soil-like material released methane after the warm probe disturbed it, consistent with a surface that had been wetted in the geological recent past. Huygens transmitted from the surface for roughly 70 minutes before Cassini moved below its radio horizon. The probe itself may have continued operating a little longer, but its data could no longer reach the orbiter. It remains the only successful landing on a world in the outer solar system. The landing site was not beside one of Titan's great seas. It was in an equatorial region that often appears dry. Yet the channels, rounded ice cobbles, and damp ground demonstrated that liquid methane can sometimes transform even Titan's lower latitudes. Cassini continued the exploration for another 12 years. Titan was more than a destination. It was also a tool. The moon's gravity repeatedly changed Cassini's orbit, allowing the spacecraft to visit different parts of the Saturn system without carrying an impossible amount of fuel. Each close encounter could bend the trajectory and set up later observations of Saturn, the rings, Enceladus, and other moons. Cassini completed more than 100 targeted Titan flybys. During them, radar mapped broad portions of the surface. Infrared instruments examined composition and clouds. Cameras monitored haze and seasons. Radio science probed the atmosphere and interior. Gravity measurements revealed how Titan deforms under Saturn's pull. The result was not a single discovery, but the gradual appearance of a complete world. Before examining that world in detail, it helps to understand where Titan is and why its basic conditions are so unusual. Titan orbits Saturn at an average distance of about 1.2 million kilometers. This places it well beyond Saturn's main rings and outside the orbits of several large icy moons. The moon is tidally locked. It rotates once during each orbit and keeps nearly the same hemisphere facing Saturn, just as Earth's moon keeps nearly the same face toward Earth. One Titan solar day, from noon to noon, lasts almost 16 Earth days. Saturn and Titan travel around the Sun once every 29.5 Earth years. Titan therefore shares Saturn's long year. Because Saturn's rotational axis is tilted, Titan experiences seasons. Each season lasts more than 7 Earth years. The Sun seen from Titan provides only about 1% of the energy Earth receives. It would appear much smaller than in our sky. Yet the atmosphere does not simply freeze onto the ground. Several effects help set the temperature. Methane and other gases absorb infrared radiation. Haze both cools and warms different atmospheric layers. Nitrogen supplies the mass and pressure that allow methane to condense, evaporate, and flow across the surface. The final surface temperature sits near the narrow range where methane can exist as gas, liquid, or frost depending on local conditions. That balance is one reason Titan is so rare. Move the same world significantly closer to the Sun, and methane would remain mostly gaseous. Move it farther away, and more methane might freeze. Change the atmospheric pressure, and the liquid range would shift. Change the supply of methane, and the active climate could fade. Titan is about 5,150 kilometers in diameter. It is the second largest moon in the solar system after Ganymede. Mercury is slightly smaller in diameter, but Mercury contains much more rock and metal and is therefore more than twice as massive. Titan's average density suggests a mixture of rock and water ice. It likely formed within the disk of gas and solids that surrounded young Saturn more than 4 billion years ago. The exact process remains uncertain. Titan's atmosphere and isotopic composition preserve clues, but those clues have several possible interpretations. The nitrogen may have originated partly in ammonia-bearing ices incorporated during formation. Chemical processing and heating could later have converted ammonia into molecular nitrogen. Some gases may have been released from the interior. Impacts may have added or removed material. The present atmosphere is the result of formation, escape, chemistry, geology, and time rather than one simple event. Titan's surface gravity is only about 14% of Earth's. A 70-kilogram person would retain the same mass, but weigh roughly as much as a 10-kilogram object weighs on Earth. Falling would be slower once the dense atmosphere created strong drag. With suitable equipment, Titan would be one of the most favorable known solid worlds for powered flight. That combination of low gravity and dense air is what makes Dragonfly possible. It also shapes natural processes. Small particles can remain suspended. Winds that seem modest can move organic grains. Parachutes are effective. Clouds can tower through a deep atmosphere. Rain falls slowly compared with heavy terrestrial rain. Although individual storms may still deliver substantial amounts of liquid, the atmosphere extends far above the surface. There is no sharp boundary where it simply ends. Density decreases gradually with altitude. Because Titan's gravity is weak and the upper atmosphere is warm relative to the surface, the atmospheric envelope is physically extended. Haze layers reach hundreds of kilometers upward. Near the ground, nitrogen accounts for most of the gas. Methane contributes several percent, with the precise fraction changing with altitude and humidity. Hydrogen, ethane, acetylene, propane, hydrogen cyanide, nitriles, and many other species occur in smaller amounts. Calling them trace gases can make them sound unimportant. On Titan, they control much of the visible world. Methane drives weather. Photochemical products make the haze. Condensed organics build surface deposits. Minor atmospheric ingredients can become major geological materials when integrated across millions of years. The lower atmosphere is the troposphere, where temperature generally decreases with height and weather occurs. Methane can condense into clouds there. Above lies a warmer stratosphere, heated partly because haze absorbs sunlight. Higher still, the mesosphere and thermosphere respond to ultraviolet radiation, particles from Saturn's magnetic environment, and changing solar conditions. Titan's atmosphere also rotates in a complex way. Near the surface, winds measured by Huygens were gentle. Higher in the atmosphere, winds become much faster. Much of the atmosphere superrotates, circling Titan more rapidly than the solid moon turns beneath it. Superrotation also occurs on Venus and in parts of Earth's atmosphere, but maintaining it requires the transfer of angular momentum through waves, tides, and circulation. On Titan, seasonal heating, haze, and the long day all contribute. Huygens drifted sideways by more than 100 kilometers during descent. Its radio signal and onboard measurements trace changes in wind direction and speed. Near one altitude, the probe encountered unexpectedly weak winds before stronger flow returned below. The atmosphere is dynamic even when the orange globe appears calm from space. At the poles, winter brings darkness that lasts for years. Air cools and sinks. A large polar vortex develops, isolating gases within a rotating circulation. Compounds produced higher in the atmosphere can become concentrated and condense into unusual ice clouds. As seasons change, the vortex weakens over the warming pole and forms over the pole, entering winter. Cassini watched this transfer. When the spacecraft arrived, Titan's northern hemisphere was in winter. A broad hood of haze covered the north. During the mission, northern spring arrived. The northern atmosphere warmed, and circulation reorganized. Later, a rapidly developing vortex appeared over the south as that hemisphere moved toward winter. The speed of the southern transition surprised researchers. Trace gases accumulated, and high-altitude clouds formed where temperatures fell much lower than some models had expected. Titan's climate is therefore not a static orange fog. It breathes over decades. A season lasts longer than many space missions. Cassini observed nearly half a Titan year, an extraordinary achievement, yet it still captured only part of the full cycle. The haze has cycles of its own. From a distance, Titan often shows a main golden layer and thinner detached layers above it. The altitude of the detached haze changes with season. Small particles are created high in the atmosphere, grow, settle, merge, and sometimes become incorporated into clouds. The chemistry begins when sunlight or energetic electrons break methane and nitrogen molecules apart. Methane becomes fragments, such as the methyl radical. Nitrogen becomes reactive atoms and ions. These pieces collide and form new molecules. Some products remain relatively simple, including ethane and acetylene. Others contain nitrogen, such as hydrogen cyanide. Reactions proceed toward aromatic rings, longer chains, and particles containing hundreds or thousands of atoms. Results published in 2025 from James Webb Space Telescope observations made in 2022 and 2023 provided the first definitive detection of the methyl radical in Titan's atmosphere. The molecule is short-lived and highly reactive. Detecting it was like observing an intermediate step rather than only the original methane and the stable products formed later. Webb and the Keck Observatory also followed methane clouds over Titan's northern hemisphere. Their changing altitude provided the first evidence of cloud convection in the north, above the region containing the Great Seas. These observations continued the work of Cassini from a distance. Titan remained active after the spacecraft was gone. The solid haze particles are often called tholins. Tholin is not the name of one molecule. It is a broad laboratory term for complex organic mixtures created when energy acts on simple carbon and nitrogen-bearing gases. Different starting mixtures and energy sources produce different tholins. Laboratory Titan simulations create brown or reddish material that resembles aspects of the atmospheric haze. The particles can contain nitriles, hydrocarbons, aromatic compounds, and more complex structures. It is tempting to call tholins the building blocks of life. The phrase needs care. Organic does not mean biological, and complexity does not mean life is about to appear. Many organic reactions occur naturally without biology. The importance of Titan's material is that it represents chemical potential. When organic particles interact with liquid water under laboratory conditions, especially after heating or hydrolysis, they can yield compounds including amino acids and other molecules relevant to prebiotic chemistry. Titan's frozen surface usually prevents such water-based reactions, but impacts can melt ice. Possible cryovolcanic processes could expose warm water ammonia mixtures. Within those temporary environments, atmospheric organics and liquid water may meet. Titan has therefore been running one part of a prebiotic chemistry experiment on a planetary scale. The atmosphere manufactures and sorts carbon-bearing material. The surface stores it in cold conditions. Geological events occasionally alter it. The total supply may be enormous. Particles settle slowly from the sky. Some become part of the dunes. Some collect on plains. Some dissolve in methane and ethane. Some are transported by rainfall and rivers. Some may sink through seas or form evaporite-like deposits along retreating shorelines. The orange haze is not merely something that hides Titan. It is one of the processes building Titan's surface. The haze also changes the light. At visible wavelengths, an observer on the ground would not see a blue sky. Daylight would be diffuse and orange-brown. The sun might appear as a bright patch or small disk under favorable conditions, but its light would be heavily filtered. Night would still exist. Titan turns slowly beneath the sun, and the night side receives no direct sunlight. The sky would grow dark, although haze, Saturn shine, and scattered light could affect brightness. Stars would be difficult or impossible to see through most of the visible haze. There is no perpetual daylight and no perpetual twilight everywhere. There is a long cycle of dim day and dark night, each lasting many Earth days. Saturn would also not simply hang high in an open black sky. From the hemisphere of Titan facing Saturn, the planet remains in nearly the same part of the sky because Titan is tidally locked. Saturn would span roughly 5.5 degrees, about 11 times the apparent diameter of the full moon seen from Earth. But the visible haze would usually hide it from human eyes at the surface. Titan orbits close to Saturn's equatorial plane. From Titan, the rings would be viewed nearly edge-on, not spread wide like the familiar pictures taken from above Saturn's equator. At wavelengths that penetrate the haze, Saturn would appear enormous, with the rings compressed into a thin line. On Titan's far hemisphere, Saturn would never rise at all. This quiet geometry has existed for billions of years. One side, turned toward the giant planet, the other turned away, while both experienced the distant movement of the sun through long days and seasons. Beneath the sky, the atmosphere meets a landscape that Cassini revealed piece by piece. Radar did not return ordinary photographs. It transmitted radio pulses and measured the strength and timing of echoes. Smooth liquid surfaces often appeared dark because they reflected energy away from the spacecraft. Rough terrain appeared bright. Slopes facing the radar could brighten dramatically. Composition, roughness, and geometry all influenced the result. Interpreting the images required care. A dark patch might be liquid, smooth sediment, or radar shadow. A bright region might be rough ice, a favorable slope, or a different material. Confidence grew when multiple observations agreed. Radar darkness, shoreline shapes, infrared behavior, specular reflections, and altimetry. By the end of Cassini's mission, the broad pattern was clear. Titan possessed equatorial dune seas, extensive plains, bright dissected uplands, mountains, labyrinth terrain, impact craters, river channels, polar lake districts, and 3 great northern seas. The landscape looked neither young nor ancient in one simple sense. Some terrains preserved craters. Others had been buried or eroded. Titan was active enough to alter its surface, but not active in the same way or at the same speed everywhere. Its geography had become a history of weather written into ice and organic sediment. Across Titan's equatorial belt, the most extensive landscapes are dark dune fields. They cover an area comparable to several large terrestrial deserts combined. Individual dunes can rise around 100 meters and extend for many tens or hundreds of kilometers. They often run roughly parallel to one another, separated by brighter corridors where the underlying ground is exposed. The grains are likely close to the size of coarse terrestrial sand, but their composition and history are different. They may include atmospheric organic particles that settled, became coated, clumped together, broke apart, and were repeatedly transported. Some water ice grains may be present, but the dark spectral character points strongly toward carbon-rich material. Making sand on Titan is not simple. Fresh haze particles are much smaller than sand grains. They must grow without becoming permanently cemented into large solid masses. One possibility is that they collect into fragile aggregates. Another is that organic material coats ice fragments. Repeated wetting, drying, abrasion, and chemical alteration may help maintain grains of movable size. The dunes record wind directions over long intervals. Their broad east-west orientation originally seemed inconsistent with models predicting average near-surface winds in the opposite direction. The puzzle led to a more complete picture. Most of the time, winds near the equator may be gentle. Around equinox, however, rare strong methane storms can generate gusts from the west. Those brief events may do most of the work of moving the sand. A desert can therefore be shaped not by the ordinary daily breeze, but by storms separated by years. The dune shapes are influenced by topography. They bend around bright uplands and split around obstacles. This makes them tracers of both wind and terrain. By following their curves, researchers infer how air flows around mountains and through corridors. The dark equatorial region called Shangri-La contains broad dune seas. The brighter region Xanadu interrupts them. Xanadu is roughly continent-sized. Radar images show rugged terrain, branching valleys, mountain belts, and areas dissected by erosion. Its origin is not fully understood. It may expose older crustal material that stands above surrounding plains. Tectonic deformation, impacts, and erosion may all have contributed. Other bright terrains form isolated uplands, sometimes compared with islands rising from dark sand seas. They are not islands in liquid. They are topographic or compositional highs surrounded by dune material. Titan also has mountains. They are modest compared with the highest mountains on Earth or Mars, but they matter because Titan's icy crust cannot support unlimited relief. Chains near the equator rise 1 or 2 kilometers above their surroundings. Some ridges may have formed by compression as the crust responded to changes in the interior. Others may be remnants of impact structures or tectonic blocks. Water ice at 94 Kelvin behaves as a strong geological material. It can fracture, fold, and support mountains over long periods. However, ice can also flow and relax under stress. The balance between strength and slow deformation helps explain why Titan's relief is generally subdued. Much of the surface consists of broad plains. Some plains are relatively uniform in radar images and may be covered by layers of organic sediment. Others show channels, hummocks, or low ridges. Plains could form through the deposition of atmospheric material, flooding by liquid hydrocarbons, cryovolcanic resurfacing, or the erosion of older terrain. Distinguishing among those origins is difficult from orbit. Cassini mapped only part of Titan at its highest radar resolution. Some regions were observed once from one direction. Lighting and radar geometry changed. Features that look smooth at kilometer scales may be complex on the ground. Dragonfly will provide a different scale of observation. Its cameras will see grains, slopes, layers, and small channels that no orbital radar could resolve. Impact craters are uncommon, but scientifically valuable. Titan must have been struck throughout solar system history. Yet only a limited number of convincing craters have been identified. The atmosphere destroys or slows smaller incoming bodies. Larger impacts still reach the surface, but later erosion, sedimentation, and viscous relaxation can disguise the scars. A crater on Titan is not simply a hole. The impact excavates water ice and deeper material. The energy can melt part of the icy crust, creating a temporary pool of liquid water. Organic material from the surface and atmosphere can fall into that melt. For thousands or perhaps tens of thousands of years, depending on crater size and conditions, liquid water and complex carbon-bearing compounds may coexist before the pool freezes. Those environments are central to Dragonfly's science. Selk is one of Titan's well-preserved impact craters. It is about 80 kilometers wide and lies within reach of the planned exploration region. Its morphology suggests that an impact exposed and melted icy material. The crater is old enough that the melt is no longer liquid, but chemical products created during the warm interval may remain preserved. The history of that chemistry could answer a subtle question. Titan's atmosphere produces organics continuously, but the surface is too cold for many reactions that proceed easily in water. An impact provides heat and water without requiring a long-lived warm climate. If the resulting mixture creates amino acids, nitrogen-bearing compounds, or other prebiotic products, Titan may reveal how far non-living chemistry can advance during temporary windows of opportunity. Other craters preserve information about crustal structure. Their depths, rims, central peaks, and degraded shapes show how the ice responds to impacts. Some are filled with sediment. Some may have been modified by methane rain. Others appear shallower than comparable craters on airless moons because the crust relaxed or material accumulated within them. The rarity of craters also limits precise surface dating. On the Moon, crater counts can be calibrated against samples returned to Earth. Titan has no returned samples, and the atmosphere filters the impactor population. Estimates of terrain age, therefore, contain substantial uncertainty. Still, Titan is clearly not a surface untouched for 4 billion years. Wind and liquid have worked across it. Organic material has accumulated. Some terrains have been deformed. The polar regions have developed landscapes unlike anything elsewhere. The first convincing lakes were found near the North Pole. Cassini radar images showed dark shapes with sharp shorelines, islands, bays, channels, and smooth interiors. Their forms were too systematic to dismiss as ordinary plains. Later observations detected reflections resembling sunlight glinting from liquid. Titan became the only known world other than Earth with stable bodies of liquid on its surface. The liquid is mainly methane and ethane, with dissolved nitrogen and smaller amounts of other hydrocarbons. The exact composition differs between bodies and may change with depth, season, and evaporation. 3 great seas dominate the north. Kraken Mare is the largest, extending more than 1,000 kilometers from end to end and covering roughly 400,000 square kilometers when connected bays and basins are included. Its intricate coastline contains islands, peninsulas, drowned valleys, and narrow straits. Ligeia Mare is smaller but still comparable in area to one of Earth's great inland seas. Radar signals penetrated portions of it and reflected from the bottom, showing depths reaching at least around 160 meters in measured regions. The liquid appears to be especially rich in methane. Hunga Mare is the 3rd major sea. Around them lie many smaller lakes. Some have rounded or irregular outlines. Some occupy steep-sided depressions and seem to sit above the regional sea level, like lakes perched within high terrain. A number are more than 100 meters deep despite their limited width. These deep lakes pose a geological puzzle. On Earth, steep depressions can form by volcanic collapse, glacial processes, impact, or the dissolution of soluble rock. Titan's polar lake basins may have developed partly through the dissolution or collapse of organic-rich surface materials, in a process loosely analogous to karst landscapes on Earth. The analogy should not be taken too literally. The soluble materials are different, the liquids are hydrocarbons, and Titan's temperature changes reaction rates. Yet the landscape may involve the removal of solid material by contact with liquid methane. Some empty depressions contain bright deposits around their edges. These may be evaporites, substances once dissolved in hydrocarbon liquid and left behind when the liquid evaporated. On Earth, drying salt lakes leave minerals. On Titan, receding methane or ethane can leave organic compounds. The shorelines of the large seas also record changing liquid levels. River valleys enter them, and sometimes continue below the present surface, suggesting flooding. Terraces and coastal forms may preserve earlier stands. The seas may rise and fall with seasons, climate cycles, and exchanges with underground reservoirs. Titan's northern and southern hemispheres are strikingly unequal. The north contains most of the large seas and known lakes. The south contains fewer, with Ontario Lacus as its most prominent present body. Part of the difference is seasonal. Methane can evaporate from the summer hemisphere, move through the atmosphere, and fall in the winter hemisphere. Over one Titan year, some liquid shifts between poles. But seasonal transport alone may not explain the long-term asymmetry. Saturn's orbit is slightly eccentric. The southern summer is shorter and more intense than the northern summer, because Saturn is closer to the Sun during part of that season. Across tens of thousands of years, slow changes in orbital geometry may reverse which pole receives more net liquid. The present northern seas may therefore be one phase of a much longer climate cycle. In another era, the south may have held the larger reservoirs. The total volume of surface liquid is only one part of Titan's methane inventory. Hydrocarbons may also fill pores beneath the ground, forming reservoirs sometimes called alcanifers by analogy with aquifers. Liquid could seep between lakes, exchange with the seas, or become trapped within layers of porous ice and organic sediment. Some models suggest that methane entering the crust can alter clathrate hydrates, crystalline structures in which water ice cages contain gas molecules. Exchanges among methane, ethane, nitrogen, and clathrates could change the composition of subsurface and surface liquids. The shoreline is therefore not a simple boundary between solid land and an isolated lake. It may be part of a connected atmospheric, surface, and underground system. Cassini discovered temporary bright features within Ligeia Mare that became known informally as magic islands. A feature would appear in one radar observation and be absent in another. It might change shape or brightness over time. Several explanations remain possible. Waves could roughen the surface and produce a stronger radar echo. Bubbles of nitrogen could rise from the liquid. Floating or suspended solids could gather into temporary patches. Changes in shoreline exposure might create apparent features. The available data do not select one answer with certainty. The mystery illustrates how little direct information one radar image provides. Titan's seas are not necessarily still black mirrors. They may have currents, waves, bubbles, rain, fog, floating material, and layered compositions. Yet waves appear to be generally modest. Titan's gravity is weak, but surface tension and viscosity differ from terrestrial water. Winds near the ground are often gentle. Cassini found many sea surfaces remarkably smooth at the moments observed. Seasonal storms could produce larger waves. Narrow straits may develop tides and currents as Saturn's gravity deforms Titan and liquid moves between connected basins. Kraken Mare may contain channels where tidal flow becomes especially important. One narrow passage, Beta Freedom, links parts of the sea. Models suggest currents there could be stronger than across open basins. The depth of Kraken Mare is only partly measured. Near one coastal river mouth, radar reached the bottom at depths of roughly 20 to 35 meters. In central regions, no bottom reflection was detected. That absence could mean the sea is much deeper, the liquid absorbs the signal, or the bottom is too rough or compositionally different. Later analyses have suggested that some parts may be hundreds of meters deep, but the precise maximum remains uncertain. The seas are cold enough that a human-made vessel would face unfamiliar engineering conditions. Liquid methane is less dense than water. Materials behave differently at cryogenic temperature. The atmosphere above is dense, and winds are slow. A floating probe could potentially survive, but no mission has yet sailed Titan's seas. The site would be unlike any earthly coast. The liquid would probably appear dark. The sky would be orange. Ice cliffs or organic-covered plains might meet the shore. Rain could arrive in rare showers. Fog might form above the liquid as methane exchanges heat and vapor with the air. Sunlight would be weak but not absent. Under the right geometry, it could produce a muted glint through atmospheric windows. The rivers feeding the seas are equally remarkable. Some channels begin in uplands and branch like terrestrial river networks. Others appear as broad valleys that may have carried catastrophic floods. At high latitudes, rivers flow toward persistent lakes. Near the equator, channels may remain dry for long intervals and activate during intense storms. One of the largest known drainage systems, Vid Flumina, enters Ligeia Mare. Radar altimetry showed steep-sided canyons hundreds of meters deep, filled with liquid in their lower portions. They resemble drowned river valleys, though their walls and floors are made from icy and organic materials. The canyons may have formed as rivers cut downward while sea level changed or the crust moved. Their existence demonstrates that methane flow can produce substantial erosion. Erosion on Titan operates under unfamiliar conditions. Liquid methane is less dense and less viscous than water. Water ice bedrock is strong at the surface temperature. Organic sediment can be soft or cohesive. Gravity is low. Rainfall is intermittent. A Titan river may therefore carry sediment differently from an Earth river. It may need greater flow depth or stronger floods to move large ice cobbles. Once moving, however, the lower gravity may allow particles to remain transported for longer distances. Huygens showed rounded cobbles at its landing site. Orbital images show channels extending across hundreds of kilometers. Together, they indicate that erosion is not merely theoretical. The methane rain responsible for that erosion is uneven. Titan can experience long dry periods. Methane humidity builds. Clouds form under favorable circulation. A storm may then release intense rain over a regional area. Cassini observed clouds appear, grow, and dissipate. It also detected surface changes consistent with wetting after major cloud events. Near the South Pole, terrain darkened after a storm and later brightened as liquid evaporated or drained. No camera has followed individual methane droplets all the way from cloud to ground. The evidence comes from clouds, atmospheric measurements, wet surfaces, channels, lakes, and climate physics. Together, it is compelling. The Webb and Keck results published in 2025 added evidence for active cloud convection above the northern seas. Titan's weather did not end with Cassini. The droplets themselves may be larger than typical terrestrial raindrops because of Titan's low gravity and dense air. They fall more slowly. A storm could sound gentle while still delivering enough liquid to flood channels. Methane rain may also carry dissolved or suspended organic material. As droplets descend, they pass through haze. They can collect particles and gases. On the ground, the liquid interacts with surface deposits, transports soluble compounds, and leaves different mixtures behind after evaporation. Rain is therefore a chemical process as well as a geological one. The complete methane cycle resembles Earth's water cycle at the broadest level. Liquid evaporates from seas, lakes, moist ground, and perhaps subsurface reservoirs. Vapor moves through the atmosphere. Clouds form. Rain returns methane to the ground. Rivers move it downhill. Lakes store it. Evaporation begins again. But Titan's cycle differs in important ways. The available solar energy is small. Much of the surface is dry. The main reservoirs are concentrated near the poles. Methane is chemically destroyed high in the atmosphere. Ethane and heavier products accumulate. The crust may exchange hydrocarbons with underground storage. Earth's oceans are not gradually destroyed by sunlight in the same way because water vapor cycles back efficiently and oxygen-hydrogen chemistry differs. Titan is losing methane from its active system unless geology resupplies it. Ultraviolet light breaks methane apart. Some hydrogen escapes to space. Carbon remains in ethane, acetylene, haze, and other products. Over tens of millions of years, an atmosphere with no new methane would change dramatically. The exact lifetime depends on models and reservoirs, but it is much shorter than Titan's age. The present methane must therefore be temporary or replenished. Perhaps Titan experienced episodes of outgassing. Methane trapped in clathrates or dissolved in internal liquids may have reached the surface through fractures. Large impacts may have released it. Cryovolcanic eruptions may have contributed. Subsurface hydrocarbon reservoirs may buffer the atmosphere. No active global resupply mechanism has been confirmed. This is one of Titan's deepest questions. The rivers and clouds we see may be part of a long-lived balance, or they may belong to a special geological era that will eventually end. The atmosphere may once have contained much more methane. If methane abundance increased, greenhouse warming and rainfall patterns would change. Some models produce climates with more extensive surface liquid. The broad plains and dry equatorial channels may preserve earlier conditions. Conversely, if the methane supply fades, clouds and rain will become rarer. Lakes will shrink or become richer in ethane. Dunes and haze chemistry will change. Titan's present geography is therefore a snapshot within a climate history. That history is written in the composition of the seas. Methane is relatively volatile and cycles readily through the air. Ethane is a stable product of methane photochemistry and should gradually collect at the surface. Early models expected the seas to become heavily ethane-rich over time. Measurements found that at least some, including Ligeia Mare, are strongly methane-rich. This may indicate active replenishment, mixing, rainfall, or exchange with underground reservoirs. Nitrogen dissolved in the liquid also affects density and evaporation. Krakenmeer may be more ethane-rich than Ligeia, although uncertainties remain. A future sea probe could measure temperature, composition, currents, waves, suspended particles, and depth directly. It could watch weather from the surface and listen to methane rain. Dragonfly will not visit the northern seas. Its landing region is near the equator, chosen for scientific value and safe access. The seas remain destinations for later missions. For now, Cassini's radar tracks and infrared glints are the basis of our knowledge. That limited knowledge is enough to establish something extraordinary. On a moon almost 1.5 billion kilometers from the sun, climate has organized liquid into watersheds. Rain falls on high ground. Rivers descend. Sediment moves. Canyons deepen. Lakes fill. Seas exchange vapor with clouds. The material is different, the temperature is different, and the pace is slower, but the logic of landscape continues. The surface cycle is only the uppermost layer of Titan's story. Far below the dunes and river valleys lies a water-rich interior whose structure is now less certain than it appeared only a few years ago. For more than a decade, the leading model placed a global liquid water ocean beneath the outer ice shell. Cassini had shown that Titan changes shape under Saturn's tides far more readily than an entirely cold, rigid body should. Measurements of gravity, rotation, and orientation could all be explained by an outer shell partly separated from the deeper interior by liquid. The key quantity is Titan's tidal love number, a measurement of how strongly its gravity field and shape respond as Saturn repeatedly squeezes the Moon during its slightly eccentric orbit. Earlier analyses focused mainly on the amplitude of that response. A large response appeared to favor a global ocean, perhaps tens or more than 100 kilometers below the surface. Models often placed ordinary ice above the water and denser high-pressure ice below it, potentially separating the liquid from the rocky interior. In December 2025, a new analysis of Cassini's radio tracking data added another part of the tidal signal: the delay between Saturn's pull and Titan's response. That delay revealed unexpectedly strong internal energy loss, amounting to roughly 3 to 4 trillion watts. The study's authors argued that a global liquid layer could not reproduce both the amount of deformation and the strong dissipation. Their preferred model contained no continuous ocean. Instead, much of Titan's deep water layer consisted of high-pressure ice close to its melting point, deforming like an immense mass of slush. In that model, small fractions of the deep layer remain liquid as pockets and channels of meltwater. Some pockets near the rocky interior could be surprisingly warm and chemically concentrated. The new interpretation does not turn Titan into a dry, solid moon. It replaces one global ocean with a more complicated hydrosphere containing ice crystals, dissolved material, and scattered liquid. Because every conclusion still comes from indirect geophysical measurements, the debate is not finished. Older ocean models explained important observations, while the newer slush model explains the measured tidal delay. Dragonfly's seismometer may provide an independent test. Methane and other volatiles may also be trapped within clathrate hydrates in the crust. A clathrate is an ice structure whose molecular cages hold gas. Changes in temperature and pressure can release or absorb methane. Ammonia water liquids may exist in local pockets, and porous layers may contain liquid hydrocarbons. The outer shell may have experienced convection, with warmer ice rising and colder ice sinking over geological time. All these possibilities connect the interior to the atmosphere. Titan's methane cannot survive indefinitely under sunlight. If it has been replenished, at least part of the source probably lies in the crust or deeper interior. The challenge is finding evidence that material actually reached the surface. Cryovolcanism has often been proposed. A cryovolcano erupts materials that are volatile at low temperature, such as water, ammonia, or methane, instead of silicate magma. The comparison with a terrestrial volcano is useful but imperfect. The fluids can freeze rapidly, and the driving forces may involve buoyancy, pressure, dissolved gas, or freezing-induced expansion. Several Titan features have been presented as possible cryovolcanoes. Sotra Patera is a broad depression near mountains and apparent flow-like terrain. Deux Monts rises nearby. Infrared and radar data suggest complex topography that could be consistent with an eruptive center. Other candidate regions include lobate forms, bright flows, and circular structures. None provides an unambiguous observation of active eruption. Alternative explanations include tectonic uplift, erosion, impact modification, or ordinary sedimentary processes. Titan's radar coverage and resolution are not sufficient to settle every case. The most accurate conclusion is that cryovolcanism is plausible but unconfirmed. If it occurs, it might deliver water-rich material and internal methane to the surface. Such deposits would be especially valuable for chemistry. Fresh ice could mix with atmospheric organics. Ammonia could change reaction pathways. Warm conditions might persist locally before freezing. Dragonfly is not expected to land directly on a confirmed active cryovolcano because no such site is known. Its regional measurements can still search for compositional signs of interior material and help determine whether nearby terrains have a cryovolcanic history. Titan's interior also affects its long-term evolution. Heat came initially from formation and differentiation and continues to come from radioactive decay. The 2025 tidal analysis, however, suggested that present tidal dissipation may be far stronger than previously recognized and may exceed radiogenic heating by roughly an order of magnitude. In the proposed slush model, much of that energy is released as high-pressure ice crystals deform and rub past one another. Whether Titan contains a continuous ocean or a slushy hydrosphere with isolated melt pockets, its deep water-bearing layers may be very different from the oceans of Europa or Enceladus. Ocean worlds are not a single kind of environment. Some liquids touch rock. Some are separated by high-pressure ice. Some produce plumes. Others remain sealed below hundreds of kilometers of frozen material. Titan is unusual because it certainly possesses one open liquid system at the surface, made from methane and ethane, while its deeper aqueous system may range from a global ocean to a partly melted ice mantle. Between the surface hydrocarbons and the deep hydrosphere lies a thick shell of ice, sediment, organics, clathrates, and possible reservoirs. The two systems use different solvents and different chemistry. They may interact only rarely, perhaps during large impacts, deep convection, or cryovolcanic events. This creates two different astrobiological questions. The first asks what happens when complex organic material meets liquid water, whether in an impact melt or a deep water pocket. The second asks whether chemistry in liquid methane can ever become biological. The first question is closer to known science. All life on Earth uses water. Water dissolves ions and polar molecules, supports acid-base chemistry, helps proteins fold, and participates directly in metabolism. Titan supplies abundant organic material, but keeps most surface water frozen. Impacts briefly overcome the barrier. When a large object strikes Titan, it releases enormous energy. Ice melts. A pool or subsurface lens of water forms. Rock fragments, ammonia, salts, and atmospheric organics mix within it. The liquid begins to cool immediately, but large melt deposits can persist for long periods compared with laboratory experiments. Depending on size and insulation, portions may remain liquid for thousands or tens of thousands of years. That is enough time for extensive chemistry. Laboratory studies of Titan, like haze materials, show that contact with liquid water can produce amino acids and other oxygen-bearing organic compounds. The exact results depend on starting material, temperature, pH, energy, and duration. Finding such products on Titan would not prove that life began. It would show that atmospheric chemistry can be carried farther when geological events add water. Selk Crater offers a natural test. The crater lies amid equatorial dune material rich in atmospheric organics. The impact excavated water ice and probably created a melt environment. Later sediment may have covered some deposits and protected them from radiation. Dragonfly plans to move from dune fields towards Selk during its nominal mission. It can compare ordinary organic sand with material influenced by impact processing. A difference between those sites could reconstruct a sequence. First, methane and nitrogen react in the atmosphere. Then particles settle. Wind gathers them into dunes. An impact melts ice. Water and organics mix. The mixture freezes. Millions of years later, a spacecraft drills into the deposit and identifies what chemistry occurred. Few places allow so many stages to be examined within one region. Titan also preserves material well. The cold slows many reactions. There is no surface oxygen-rich environment rapidly destroying organics. Solar ultraviolet light is largely absorbed above the ground. Saturn's radiation environment at Titan is less severe at the surface than Jupiter's radiation at Europa. Preservation does not mean complete protection. Cosmic rays penetrate. Weather transports material. Methane dissolves some compounds. Impacts and erosion alter deposits. Still, Titan is a vast archive. The second astrobiological question is more speculative. Could a system resembling life operate in Titan's liquid methane or ethane? There is no evidence that it does. The question is scientifically useful because it tests which features of terrestrial life are universal and which depend specifically on water. A living system needs more than organic molecules. It requires a boundary separating itself from the environment. It needs a way to store and reproduce information. It needs reactions that capture usable energy. It needs raw materials, catalysts, and a means of maintaining organization while entropy increases around it. On Earth, membranes are built from molecules with water-loving and water-avoiding parts. In water, those molecules naturally arrange into bilayers. Liquid methane is nonpolar and cryogenic. Terrestrial membranes would not function there. Proteins would be rigid or insoluble. Familiar biochemical reaction rates would be extremely slow. Any methane-based life would need fundamentally different chemistry. In 2015, a theoretical study proposed a membrane-like structure made from small nitrogen-containing molecules, including acrylonitrile. The hypothetical membrane was called an azotosome. In 2017, astronomers using the Atacama Large Millimeter-Submillimeter Array confirmed acrylonitrile in Titan's atmosphere. The sequence was intriguing. A calculation suggested a possible material, and the real atmosphere contained the molecule. But the proposal weakened under further testing. A 2020 thermodynamic study concluded that the membrane would not self-assemble under Titan conditions. Then, in 2026, the first laboratory experiments with acrylonitrile and simulated methane and ethane lake fluids found that it tended to remain largely unchanged in methane or form a stable crystal with ethane rather than assemble into vesicles. Acrylonitrile-based azotosomes now appear unlikely to form in Titan's lakes. They remain an instructive hypothesis, not evidence of cells, and probably not a workable membrane design. Other proposals imagine metabolism using hydrogen, acetylene, or chemical gradients across lake sediments. Some researchers have examined whether surface hydrogen appears depleted in ways that could be biologically interesting. The observations have non-biological explanations and are not accepted as biosignatures. Energy is a major difficulty. Sunlight at Titan is weak, especially beneath haze and within liquid. Chemical reactions at 94 Kelvin proceed slowly unless effective catalysts exist. Methane and ethane are relatively stable. Possible energy sources include atmospheric products falling out of chemical equilibrium, ultraviolet-generated molecules, cosmic rays, and reactions involving hydrogen or acetylene. Whether those sources could sustain anything complex is unknown. The lakes also contain changing mixtures. Methane evaporates more readily than ethane. Nitrogen dissolves in the liquid. Temperature varies slightly with season and depth. Organic solutes can precipitate or accumulate at shorelines. A truly alien biology might exploit those differences. Yet the responsible position remains clear. Titan is not considered an inhabited world merely because it has organic chemistry and liquid. The surface is a test of possibility, not a discovered ecosystem. Dragonfly will not land in a lake and is not designed to identify methane-based organisms. It can still improve the question by measuring the composition and complexity of organic material, the availability of chemical energy, and environmental conditions. Its atmospheric sensors can examine how compounds are transported. Its mass spectrometer can identify molecules that reach the dunes and impact deposits. The findings may show that Titan's chemistry is richer than expected. They may also show that cold hydrocarbon environments impose severe limits. Either result would matter. Astrobiology is not only the search for a positive detection. It is the study of where and why chemistry does or does not cross certain thresholds. Titan can reveal the importance of temperature, solvent, energy, and geological mixing. It can also challenge a common misunderstanding about organic molecules. Carbon compounds occur throughout the universe. They are found in meteorites, comets, interstellar clouds, planetary atmospheres, and protoplanetary disks. Their presence is not surprising and does not by itself imply life. What matters is organization. Simple molecules must become networks. Networks must persist. Information must be copied with variation. Energy must flow through the system. Titan may contain many ingredients while lacking the conditions needed to assemble them into biology. That gap is exactly what makes the moon valuable. It allows the chemistry before life to be studied without assuming that life followed. The connection to early Earth is also subtle. Titan is sometimes described as a preserved version of primordial Earth. It is not. Early Earth was warmer, had liquid water oceans, stronger sunlight, active geology, and a different atmospheric history. Titan is much colder, and its methane-rich haze exists over an icy surface. The comparison is useful only at the level of atmospheric organic chemistry. Both environments involve nitrogen, carbon-bearing gases, energy, aerosols, and complex reactions. Titan allows some processes to be isolated and observed today. Laboratory simulations inspired by Titan can help identify how haze particles form and what they produce when mixed with water. Those results can then inform models of Earth's early atmosphere, though they cannot reproduce it exactly. Titan is therefore not a time machine. It is a parallel experiment. Its differences are as informative as its similarities. There is another way in which Titan broadens astrobiology. The traditional search for habitability often begins with the surface temperature of a rocky planet and the question of whether liquid water can remain exposed beneath a star. Titan lies far outside that classical surface habitable zone. Its surface water is frozen, yet chemistry continues through methane, weather, and internal heat. A world can therefore remain chemically active without possessing warm oceans under open sunlight. That does not make every cold moon habitable. It means that the range of environments worth investigating is wider than one narrow band around a star. Europa and Enceladus demonstrate that internal oceans can survive beneath ice. Titan adds a dense atmosphere, surface hydrocarbons, abundant organic sediment, and a deep water-rich interior whose exact state is disputed. If the 2025 slush model is correct, even a moon without a global ocean may preserve enormous volumes of liquid in warm, chemically concentrated pockets. Comparing these worlds may reveal which combinations of water, rock, energy, and transport matter most. The question is not simply where life could exist. It is how planetary systems create opportunities for complexity. On Titan, those opportunities may be brief and local. A storm fills a channel. A shoreline concentrates solutes. An impact opens a warm pool. A crack releases material from below. A haze particle carries nitrogen and carbon to the ground. Most events may end without producing anything biological. But taken together across billions of years, they create a record worth reading. Dragonfly was selected because one stationary lander could not sample that record adequately. Titan's surface is diverse. Dune grains, interdune ice, crater ejecta, channel deposits, and possible water-altered materials record different chemistry. A wheeled rover would move slowly across soft dunes and rough terrain. A rotorcraft can fly. Titan offers exceptionally favorable conditions for powered flight. The atmosphere near the ground is dense. Gravity is low. Rotor blades can generate substantial lift without extreme speed. The cold is challenging for machinery, but the aerodynamics are generous. Dragonfly has 8 rotors arranged in 4 pairs, making it a dual quadcopter. It is roughly car-sized and much heavier than the small Ingenuity helicopter flown on Mars. Unlike Ingenuity, Dragonfly carries a complete scientific laboratory and will move its entire payload from site to site. Mars and Titan present opposite flight challenges. Mars has gravity around 38% of Earth's, but an atmosphere less than 1% as dense at the surface. Ingenuity required large, rapidly spinning blades and an extremely light body. Titan has lower gravity and far denser air. The difficulty there is not producing lift. It is surviving cold, navigating through haze, communicating across the solar system, and operating for years without solar panels. Sunlight at Titan is weak, and haze reduces it further. Dragonfly will use a radioisotope power system. Heat released by the natural decay of plutonium-238 will be converted into electricity and will also help keep the spacecraft warm. The available electrical power is limited. Dragonfly will not fly continuously. It will spend much of its time on the ground, conducting science, transmitting data, and charging batteries. Flights will be planned as individual sorties. Titan's long day shapes operations. During daylight, cameras can examine terrain. At night, the vehicle can perform some analyses and recharge. Each location becomes a temporary research station. Communication with Earth will involve long delays. A radio signal takes well over an hour to cross the distance one way, depending on the positions of Earth and Saturn. Real-time piloting is impossible. Dragonfly must navigate autonomously. Before a flight, orbital maps and previous images help define a route. During flight, cameras and navigation systems track the ground, estimate motion, avoid hazards, and select safe landing areas. The atmosphere can carry haze and clouds, but near-surface visibility is expected to be sufficient for navigation over relevant distances. The first landing is planned in the Shangri-La Dune region near Titan's equator. The site offers relatively safe broad areas, abundant organic material, and access to multiple terrain types. The dunes themselves are scientifically valuable, while the brighter interdune regions may expose water ice or different sediments. From there, Dragonfly will make progressively longer flights. The current mission plan targets launch no earlier than July 2028 aboard a Falcon Heavy rocket and arrival at Titan in late 2034. The nominal surface mission is planned to last about 3.3 years. During that time, The rotorcraft can travel many tens of kilometers, giving it access to terrain separated far beyond the reach of a conventional stationary lander. Exact routes will depend on performance and discoveries. Salk Crater is the major long-term destination. Dragonfly's instrument suite is designed to investigate the environment from several directions. The Dragonfly Mass Spectrometer, known as DRAMS, will analyze chemical components and surface samples. A drill called DRACO will acquire material and transfer it into the instrument. The Gamma Ray and Neutron Spectrometer, DRAGNS, will measure bulk elemental composition without requiring every sample to be brought inside. It can help distinguish water-rich ice, organic-rich deposits, and other materials. DragonCam will provide images from the ground and air. It will map geological context, examine textures, guide sampling, and document changing conditions. The Geophysics and Meteorology Package, DRAGMET, will monitor pressure, temperature, wind, methane humidity, and other atmospheric properties. It includes seismic measurements that may reveal activity within the crust and help distinguish a global ocean from layered ice, slush, and melt pockets below. The mission will also investigate electrical properties and the behavior of the near-surface environment. Together, these instruments will connect scales. A camera sees a dune. A drill samples a grain. A mass spectrometer identifies molecules. A weather station records the wind that moved them. A gamma-ray instrument measures the bulk material beneath. A seismometer listens for the structure below all of it. This is why mobility matters. One sample can be unusual. Several sites allow comparison. If a molecule appears in dunes, crater ejecta, and an icy corridor, its distribution tells a story. If it occurs only where water once melted, that tells another. Dragonfly will not need to discover a dramatic biosignature to succeed. It may identify reaction products showing that impact meltwater drove chemistry beyond anything occurring in dry dunes. It may find that atmospheric organics are less chemically advanced than laboratory models predict. It may measure the crust and improve models of the deep hydrosphere. It may reveal how dunes form. It may discover unexpected minerals or sediments. It may record methane weather from the ground. Each result would change our understanding of Titan. The mission is technically difficult because Titan is distant and cold. Every mechanism must work at cryogenic temperature. Lubricants, electronics, cables, seals, batteries, and sampling systems must survive repeated cycles of operation. Heat from the power source must be distributed without warming sensitive samples too much. The rotors must operate in an atmosphere whose composition and density vary with temperature and altitude. Landing gear must tolerate uncertain surface firmness. The drill must handle organic sediment, hard ice, or mixtures of both. The spacecraft must remain stable during long periods with no intervention from Earth. Testing therefore requires large chambers, low temperatures, simulated atmosphere, wind facilities, and repeated autonomous flights. A mission to Titan cannot be repaired after launch. Dragonfly's journey will also differ from Cassini's. Cassini entered orbit around Saturn. Dragonfly will approach Titan directly after interplanetary cruise. It must enter the atmosphere at high speed, protected by an aeroshell. A parachute system will slow the descent. At a suitable altitude, the rotorcraft will separate and begin powered flight before reaching the ground. It will select and approach a landing site autonomously. This transition has no exact precedent. Huygens descended under parachutes and landed passively. Ingenuity began on the surface of Mars after being delivered by Perseverance. Dragonfly must change from an interplanetary capsule into a flying aircraft during descent through an alien atmosphere. Titan's density makes this possible, but the sequence must be reliable. The destination is distant enough that the launch energy and trajectory matter greatly. Falcon Heavy provides the required capability during the planned 2028 launch window. Late 2034 will mark almost 30 years since Huygens landed. The first images from Dragonfly may show a world both familiar and transformed by scale. Cassini saw broad dark regions. Dragonfly will see individual dune slopes. Huygens photographed one landing site. Dragonfly will move among many. Orbital radar suggested icy corridors. A flying camera will reveal their rocks, layers, and fractures. For a generation, Titan has existed mostly as maps made from radar strips and infrared mosaics. Dragonfly will turn portions of those maps into landscapes. Sending a chemical laboratory to Titan also requires careful attention to contamination. Spacecraft are assembled in controlled environments, but no machine built on Earth is perfectly separate from terrestrial chemistry. Oils, plastics, cleaning agents, microbes, and trace organic compounds can confuse measurements if they reach a sample. Dragonfly must therefore distinguish Titan's molecules from material carried by the spacecraft itself. Engineers document the composition of the vehicle, clean sensitive systems, monitor possible contaminants, and include blanks and calibration procedures in instrument operations. The goal is not to pretend that every terrestrial trace can be removed. It is to understand the background well enough that a genuine Titan signal can be recognized. This is especially important because the mission is searching for prebiotic chemistry rather than one simple target. A common molecule may have many possible origins. A complex molecule may fragment inside an instrument. Two compounds with similar masses may require additional separation. Surface grains may contain mixtures formed in the atmosphere, altered by radiation, dissolved in methane, and processed by impacts. Interpretation will depend on patterns rather than one dramatic reading. The relative abundances of molecules matter. Their distribution among sites matters. The association with water ice, dunes, or impact material matters. The geological setting gives chemistry meaning. Planetary protection also considers whether Earth organisms could survive and grow at the destination. Titan's surface is profoundly hostile to known active life. The temperature is far below the range in which terrestrial cells can metabolize, and liquid water is not available at the surface for sustained growth. That makes accidental biological contamination of the ordinary surface much less concerning than it would be for a warm, wet environment. The deep internal ocean is different, but Dragonfly will not approach it. The spacecraft will sample only shallow surface material. Even so, responsible exploration treats contamination seriously because Titan's chemistry is scientifically precious. A terrestrial organic residue does not need to reproduce to damage a measurement. This care reflects a wider principle. The more subtle the question, the more carefully the experiment must be designed. A camera can establish that a dune exists. A chemical instrument must establish what the dune contains, how the sample changed during collection, what the spacecraft added, and how the measured fragments relate to the original molecules. Dragonfly's greatest discoveries may therefore emerge from patient comparison rather than one instant of revelation. A sample from a dark dune can be compared with a bright interdune patch. A shallow scoop can be compared with material from slightly below the surface. One landing site can be compared with the next. Patterns repeated across distance become difficult to explain as contamination or accident. This method resembles the broader history of Titan exploration. One dark radar patch was suggestive. Many patches with shorelines, channels, reflections, and repeated observations established lakes. One unusual molecule can be intriguing. A coherent chemical system across several environments can become a planetary process. Confidence grows when independent lines of evidence meet. There is a quiet historical symmetry in the mission. Cassini-Huygens discovered the moon through a telescope. The Huygens probe descended through its atmosphere. Cassini mapped the world hidden beneath the haze. Dragonfly will move across that world under its own power. Each stage adds freedom of movement. First, a point was followed in the sky. Then a probe fell through the air. Then an orbiter returned again and again. Next, a machine will choose new horizons and fly toward them. The mission arrives during a scientifically valuable season. Titan's climate evolves slowly, and observations from Earth and space will continue before Dragonfly reaches the surface. Webb, large terrestrial telescopes, and perhaps other observatories can monitor clouds, atmospheric chemistry, and seasonal circulation. By the late 2030s, Titan will be moving through a different part of its seasonal cycle than Cassini observed at the beginning of its mission. Comparing Dragonfly weather data with Cassini and Webb will reveal change across decades. Seasonal change on Titan is not a decorative detail. It controls clouds, rainfall, haze distribution, winds, and movement of methane between hemispheres. Saturn's axis is tilted by more than 26 degrees, similar to Earth's tilt. As Saturn orbits the Sun, each hemisphere leans toward and then away from sunlight. Titan follows the same pattern. Around equinox, sunlight crosses the equator and atmospheric circulation reorganizes. Storms can become more likely at low latitudes. Winds capable of moving dunes may intensify. Near solstice, one pole experiences a long summer while the other remains in winter darkness. The winter pole develops a vortex. Air descending inside that vortex carries complex molecules downward. Temperatures fall. Compounds that are gases elsewhere condense into high-altitude clouds. Cassini observed hydrogen cyanide ice over the developing southern winter pole, despite models that had predicted warmer temperatures. The atmosphere was cooling more rapidly than expected. This offered a reminder that even after years in orbit, Titan could surprise. At the summer pole, solar heating encourages evaporation and convection. Methane clouds form over lakes and seas. Rainfall may return liquid to the surface. Results published in 2025 from Webb and Keck observations made in 2022 and 2023 showed northern cloud systems changing altitude, evidence that air and methane were rising through the atmosphere. That vertical motion is an essential part of a working methane weather cycle. The methyl radical detected by Webb revealed another kind of motion. It is produced when methane loses a hydrogen atom. Because it reacts quickly, it does not accumulate like a stable gas. Detecting it means observing chemistry while it is happening. In a sense, weather and chemistry are inseparable on Titan. Clouds transport methane. Sunlight destroys methane. Haze stores its carbon. Rain brings products downward. Rivers redistribute them. Lakes dissolve some and reject others. Dunes collect what remains. Every part of the moon participates in chemical circulation. The atmosphere also exchanges material with space. Hydrogen formed by methane destruction can escape Titan's weak gravity. Some heavier ions are carried away by interactions with Saturn's magnetosphere and the solar wind. Titan spends much of its orbit within Saturn's magnetic environment, but that protection is not constant. The moon can enter the magnetosheath or solar wind depending on conditions. Charged particles affect the upper atmosphere. Cassini flew through Titan's ionosphere and found large negative ions, some with masses far greater than expected. These may represent early steps toward haze particles. Chemistry begins at molecular scales and eventually becomes weather-darkened terrain. The nitrogen atmosphere itself also evolves. Nitrogen is more stable than methane, but it can escape slowly and become incorporated into nitriles. The ratio of nitrogen isotopes contains information about how much atmosphere has been lost. Titan may once have had a different pressure. Reconstructing that history requires models of escape, outgassing, impacts, and chemistry. No single measurement provides the answer. The atmosphere could have formed gradually rather than appearing all at once. Ammonia within Titan's building materials may have been converted to nitrogen. Heating and chemical reactions in the interior could release gases. Large impacts might open pathways. Methane may have emerged during separate episodes. Titan's climate may therefore have switched between active and quieter states. During methane-rich intervals, rainfall and erosion increase. During methane-poor intervals, haze production declines and surface liquids retreat. The dunes, channels, and seas may not all have formed under the same climate. One landscape can preserve several eras. The age of Titan's dunes is uncertain. The polar basins may be older than the present lakes. Some dry channels may record storms under a thicker methane atmosphere. Dragonfly will not date every feature directly, but local geology can reveal relationships. A dune that crosses a channel is younger than the channel. Sediment covering crater ejecta came later than the impact. A bright icy exposure cutting through dark material may reveal excavation or erosion. Layering can record repeated deposition. Small observations can order large events. The mission may also observe processes in real time. Winds could move grains. Fog could develop. Cloud shadows might pass overhead. Methane humidity could rise before rain. The ground could change after a shower. A quake could shake the sensors. Even the absence of change is informative. If dunes remain still and weather stays quiet, the landscape may be shaped mainly by rare events. Titan rewards patience because its rhythms are slow. One rotation lasts almost 16 days. One season lasts more than 7 years. 1 year lasts nearly 30 years. Atmospheric chemistry builds haze particle by particle. Methane carves ice over geological time. A spacecraft operating for a few years samples only a short interval. Yet carefully placed measurements can connect that short interval to the ancient record. A wind sensor measures present transport. A dune records past transport. A chemical sample records atmospheric reactions. A crater records an impact. A seismic signal records the interior. Together, they turn a brief visit into a history of billions of years. This is the deeper ambition of Dragonfly. It will not merely fly because flight is impressive. It will fly because Titan's questions are distributed across the landscape. To understand why those questions exist at all, it helps to return to the formation of the Saturn system. More than 4.5 billion years ago, the Sun formed from a collapsing cloud of gas and dust. Around it, a rotating disk supplied material to the planets. Far from the young Sun, temperatures were low enough for water and other volatile compounds to freeze. Saturn grew within this outer disk. As the planet accumulated gas, it was probably surrounded by a smaller disk of its own. Within that circumplanetary disk, particles collided and gathered into moons. The regular moons of Saturn formed in orderly, low-inclination orbits near the planet's equatorial plane. Titan became by far the largest. Its growth involved rock, water ice, and more volatile materials. Heat came from impacts, compression, radioactive elements, and perhaps tides. Some components separated by density. Rock tended to sink. Ice occupied higher layers. Gases escaped from warm material or became stored in the interior. The details remain debated because Titan's present structure does not reveal every step directly. Its rocky component may not have fully separated into a simple compact core. The interior could contain a hydrated, relatively low-density rocky center surrounded by high-pressure ice and liquid layers. Titan's atmosphere also complicates the history. The nitrogen isotope ratio differs from Earth's and may indicate that the nitrogen did not arrive mainly as molecular nitrogen from the solar nebula. Ammonia or other nitrogen-bearing compounds within icy building blocks may have been converted later. Methane carries additional clues. Its carbon and hydrogen isotope ratios constrain origin and processing, but they do not uniquely identify a source. Methane could be primordial in part, produced by reactions inside Titan, or released from ancient reservoirs. Argon isotopes measured by Huygens suggest that some gases came from within the Moon rather than being captured directly from the solar nebula. Titan may therefore have acquired its atmosphere through outgassing after formation. The timing matters. If a dense atmosphere appeared early, it influenced impact, erosion, and surface temperature. If methane was released in episodes, climate changed each time. Some models propose that methane remained trapped until heating or crustal evolution opened pathways. Others allow a long history of gradual supply. No surviving record provides a simple calendar. Titan's orbit also evolved. Tidal interactions transfer angular momentum between Saturn and its moons. Titan is slowly moving outward from Saturn. Measurements of its present migration rate suggest that the evolution may be more rapid than older tidal models assumed. The Moon's current distance may therefore not represent where it formed. Orbital migration changes tidal heating, resonances, and interactions with other moons. Titan also appears to dissipate far more tidal energy internally than older models assumed. If the 2025 measurement is correct, its present orbital eccentricity should fade on a timescale far shorter than the age of the solar system. The eccentricity may therefore have been excited relatively recently by orbital interactions, the loss of another Saturnian moon, or a major collision. These possibilities remain under investigation. Titan is not heated as violently at the surface as Enceladus, yet its deep high-pressure ice may be deforming and generating several trillion watts of heat. Its present orbit and interior evolution are linked. Cassini repeatedly used Titan flybys because the Moon is massive. Its gravitational influence can alter spacecraft velocity by large amounts. In nature, the same mass affects smaller moons and particles over long periods. Titan's atmosphere may even interact weakly with Saturn's magnetosphere, creating a complex wake of plasma. The Moon is planetary in scale. Calling it a satellite describes its orbit, not its complexity. Its diameter exceeds Mercury's, although its lower density gives it far less mass. Its atmosphere, climate, water-rich interior, and geology are studied with the same methods used for planets. The comparison with Mercury shows how size alone does not determine a world's character. Mercury lies close to the Sun. It is dense, metallic, nearly airless, and heavily cratered. Titan lies in the outer solar system. It contains abundant ice, supports a dense atmosphere, and has active weather. Two bodies of similar diameter can become opposites because of composition, temperature, gravity, and history. The comparison with Earth is equally revealing. Earth and Titan both possess nitrogen-dominated atmospheres, clouds, rain, rivers, seas, dunes, and seasonal circulation. But Earth's atmospheric nitrogen coexists with oxygen produced by life. Titan's atmosphere contains methane in a reducing chemical environment with almost no free oxygen. Earth's surface liquids are water. Titan's are hydrocarbons. Earth's crust is silicate rock. Titan's surface bedrock is largely water ice mixed with organics. Earth receives intense sunlight. Titan receives about 1% as much. The similarities arise from physical processes that do not care which material is involved. Gravity pulls liquid downhill. Winds move grains. Evaporation transfers molecules to the air. Cooling produces condensation. Flowing liquid cuts channels. The differences arise because each world selects a different substance to perform the cycle. This is one reason Titan is scientifically powerful. It allows general principles to be separated from terrestrial details. A river does not require water. A dune does not require quartz. A shoreline does not require an ocean like ours. Weather does not require warm air. Planetary geology can be familiar in shape and alien in substance. Titan also provides a comparison with Venus. Both have dense atmospheres and surfaces hidden from ordinary visible light observation. Radar became essential for mapping both. Yet Venus is extremely hot and dominated by carbon dioxide. Titan is extremely cold and dominated by nitrogen. On Venus, water is scarce and sulfuric acid clouds occupy the atmosphere. On Titan, methane and organic haze dominate the visible climate. A dense atmosphere can therefore lead to very different worlds depending on sunlight, composition, and surface pressure. Mars provides another contrast. Mars has channels, deltas, and lake basins formed by liquid water in the past, but its present atmosphere is thin and stable surface water is rare. Titan has active surface liquid today, though the liquid is methane and ethane. Mars preserves a hydrologic past. Titan displays an ongoing hydrocarbon present. Pluto offers a colder comparison. Pluto has nitrogen, methane, and carbon monoxide ices. It supports a thin seasonal atmosphere and active glacial geology, but its surface pressure is far below Titan's. Methane cannot form the same open river and sea cycle there. Titan sits in a narrow environmental balance between worlds. It is cold enough for hydrocarbons to condense, but warm and pressurized enough for them to flow. It is massive enough to retain nitrogen. It has enough methane to create weather. It has enough energy to drive circulation. It has enough geological time to build complex terrain. Changing any of those conditions could remove the lakes. This makes Titan valuable in the study of exoplanets. Astronomers have found worlds at many temperatures and sizes, including planets with hazes and methane-rich atmospheres. Directly resolving their surfaces is usually impossible. Titan is a nearby laboratory for understanding how photochemical haze affects climate and observation. Haze can warm some atmospheric layers while cooling the surface by blocking sunlight. It can flatten spectral features, making gases harder to detect. It can create false simplicity when a world is actually chemically rich. When future telescopes examine a hazy exoplanet, Titan provides lessons in interpretation. A featureless orange spectrum does not imply a featureless planet. Beneath haze may lie weather, chemistry, and geology invisible to remote instruments. Titan also demonstrates that methane can have several meanings. On Earth, atmospheric methane is strongly associated with biology, though geological sources also exist. On Titan, methane is abundant without evidence of life. A methane detection on an exoplanet is therefore not automatically a biosignature. Context matters. The atmosphere's temperature, composition, ultraviolet environment, and geological sources must be considered. Methane combined with other gases far from chemical equilibrium may be more informative than methane alone. Titan is a warning against simple conclusions and a guide toward better ones. Its organic haze provides the same lesson. Organic molecules are common products of chemistry. They can become very complex without cells. The path from carbon chemistry to life is not one inevitable step. There may be many stages, barriers, and dead ends. Titan allows some of those stages to accumulate in plain view. The haze particles fall continuously, but biology has not announced itself. Perhaps life requires warm water and rapid reactions. Perhaps it requires mineral surfaces, energy gradients, wet-dry cycles, or long-term access to phosphorus and metals. Perhaps methane-based biology is possible, but exceedingly rare. Perhaps Titan contains processes we have not yet recognized. Science must hold all these possibilities at different levels of confidence. The strongest facts are observational. Titan has a dense nitrogen atmosphere. Methane clouds form. Hydrocarbon lakes and seas occupy the poles. Channels cross the surface. Organic aerosols fill the haze. A deep water-rich hydrosphere is strongly indicated, but whether it forms a global ocean or mostly slushy high-pressure ice is now disputed. The next level consists of well-supported interpretations. Methane rain carved many valleys. Dunes are made largely of organic rich grains. The atmosphere destroys methane on timescales shorter than Titan's age. Impacts produce temporary liquid water environments. The most uncertain level contains active cryovolcanism, methane-based biology, and the precise source of atmospheric methane. A good account of Titan preserves these boundaries. Mystery becomes more interesting, not less, when it is described honestly. The unknowns are specific enough to investigate. How thick is the ice shell? Does a global ocean exist? Or is the deep interior mostly slush and melt pockets? How are dune grains manufactured? How often does it rain at the equator? What controls polar lake asymmetry? Where does atmospheric methane come from? How complex are the surface organics? What products formed in Selk's impact melt? Are there active exchanges between the crust and atmosphere? These questions connect instruments to places. A seismometer addresses the deep hydrosphere. A mass spectrometer addresses chemistry. Weather sensors address rain and circulation. Cameras address geology. Repeated flights address diversity. Dragonfly is designed around the map of uncertainty. Other future missions could extend the exploration. An orbiter equipped with modern radar could map Titan globally at far higher resolution than Cassini. Precise measurements of tides and rotation could test whether a global ocean exists. A balloon could drift through the atmosphere for months, following winds and sampling haze. A lake lander could float on Kraken Mare or Ligeia Mare, measuring waves, depths, and composition. A submarine could descend beneath a hydrocarbon sea. A network of weather stations could follow a full seasonal transition. An impactor or deep ice probe might one day investigate the water-rich interior, though reaching liquid pockets or any surviving ocean would be extraordinarily difficult. These concepts remain proposals rather than approved missions. Dragonfly is the next committed step. Its success may determine what comes after. If the equatorial surface reveals abundant prebiotic products, future missions may target impact craters and icy exposures. If methane resupply signatures appear, attention may shift toward candidate cryovolcanic regions. If seismic data distinguish a global ocean from a layered slushy interior, the entire strategy for future exploration will change. If weather measurements reveal active storms, atmospheric platforms may gain priority. One mission changes the questions for the next. Cassini-Huygens did exactly that. Before Cassini, the presence of surface seas was uncertain. After Cassini, their geography became a major field. Before Huygens, the texture of the ground was unknown. After Huygens, rounded ice cobbles and drainage channels became real landscapes. The mission did not finish Titan. It made Titan larger. Every answer opened a more detailed mystery. The seas existed, but how deep were they? The dunes existed, but how did grains form? The atmosphere contained methane, but what replaced it? The crust flexed, but what structure lay beneath it? The surface held organics, but what chemistry had occurred? Dragonfly will inherit these questions and create new ones. That is the normal rhythm of exploration. A world first appears simple because it is distant. Better instruments reveal complexity. Complexity creates narrower, deeper questions. The unknown does not shrink to nothing. It becomes more precise. Titan has followed this pattern more dramatically than almost any other world. It began as a point beside Saturn. It became an orange sphere, then a moon with air, then a hidden landscape, then a world with continents, deserts, rivers, lakes, seas, weather, seasons, and a mysterious water-rich interior beneath ice. The next stage will be intimate. A machine will stand on the dunes and examine their grains. It will rise into the air. It will watch the ground move beneath it. It will land where no spacecraft has landed before. It will repeat the process across a world once considered inaccessible. Imagine for a moment, standing on Titan. A protective suit surrounds you, because the atmosphere contains no breathable oxygen and the cold would be fatal. Yet the pressure outside is not crushing. It is only moderately higher than sea level pressure on Earth. The air is dense. If you moved an arm, the atmosphere would resist more strongly than terrestrial air. A falling object would descend slowly. With broad artificial wings and sufficient strength, a person might glide in Titan's low gravity, though such a flight would remain dangerous and impractical without specialized equipment. The ground beneath you could be a dark dune. It might yield slightly underfoot, not like soft beach sand exactly, but as a surface made from cold organic grains with unfamiliar cohesion. Between dunes, brighter patches of water ice could appear like stone. The temperature would remain near minus 180 degrees Celsius. Water would not melt, splash, or feel like snow. It would form the structural material of the landscape. The sky during the long day would be orange-brown. Light would come from many directions after scattering through haze. Shadows might be soft. The sun would be small and dim, perhaps seen only as a brighter region through the atmosphere. There would be no blue overhead and no distant clear horizon. At night, the orange daylight would fade into darkness. Stars would remain hidden at visible wavelengths. The silence would not be complete. Wind could move across the dunes. Grains might slide. The structure of a spacecraft would creak as temperatures changed. If the location were on Titan's Saturn-facing hemisphere, the giant planet would occupy a fixed region above the horizon, but the haze would usually conceal it. With an instrument able to see through the atmosphere, Saturn would appear more than 10 times wider than Earth's full moon. The rings would be seen close to edge-on, forming a thin, bright line. The planet would not rise and set each Titan day. Tidal locking would keep it nearly stationary while the distant sun crossed the sky. From the far hemisphere, Saturn would remain forever below the horizon. The emotional image of a ringed planet hanging over every Titan landscape is therefore only partly true. Like many attractive images of other worlds, it must be adjusted by geometry and atmosphere. Titan is remarkable enough without changing it. Suppose the imagined location were near the equator, where Huygens landed and Dragonfly will explore. The nearest Great Sea would be thousands of kilometers away. The landscape would more likely contain dunes, plains, icy corridors, and dry channels. Rain might not fall for years. Then atmospheric conditions could change. Methane clouds could gather. The sky might darken slightly. Large droplets would descend slowly through the dense air. The dry surface would become wet. Liquid would collect in hollows, move between grains, and begin flowing into channels. A broad storm could produce flash floods even in a desert. Organic material would dissolve or become suspended. Dunes might slump. Ice cobbles could move in strong currents. Lowlands could hold shallow pools before the liquid soaked into the ground or returned to the atmosphere. Weeks or months later, much of the visible evidence might fade. The channels would remain. Farther north, the cycle would connect to permanent lakes and seas. Imagine standing on the shore of Ligeia Mare. The surface might be extraordinarily smooth beneath gentle winds. It would not be blue. Under Titan's light and haze, it might appear nearly black or dark brown. Liquid methane would lap against a shore made from water ice and organic sediment. A river canyon could open nearby, carrying liquid from higher ground. Fog might hover where the sea exchanges methane with colder air. Rain rings could spread across the surface during a storm. Ordinary solid water ice is denser than liquid methane and would tend to sink, unlike ice floating in a terrestrial ocean. Porous ice, trapped gas, organic coatings, dissolved nitrogen, and ethane could alter the behavior of natural fragments. Bubbles might rise if temperature or pressure changed. Along a retreating shore, dissolved compounds could crystallize into bright deposits. The sea would be a chemical solution, not a pure substance. Below the surface, darkness would deepen quickly. The liquid might extend for hundreds of meters. Currents would move slowly through broad basins and more rapidly in straits. No organism has been detected there. No instrument has sampled the liquid directly. The sea remains known through radar echoes, infrared observations, and models. Its mystery is not an invitation to assume life. It is an invitation to measure. Now imagine the same world during a different season. The pole tips into years of darkness. The atmosphere cools. A vortex strengthens overhead. Trace compounds descend and condense into clouds of exotic ice. At the opposite pole, sunlight returns. Methane evaporates. Clouds build. Rainfall patterns shift. Titan's climate moves on a timescale long compared with a human year, but short compared with geology. Cassini entered during one phase and departed during another. Dragonfly will arrive during another still. The two missions will not see the same Titan. This is scientifically valuable. A planet or moon cannot be understood from one season any more than Earth's climate could be understood from 1 month. Long observations reveal circulation, delay, storage, and change. Titan stores seasonal memory in its seas and ground. A storm can wet the surface. A lake can preserve liquid through many seasons. A dune can record winds over centuries. A canyon can record erosion over millions of years. The atmosphere links these timescales. A methane molecule may evaporate, become a cloud droplet, fall as rain, enter a river, reach a sea, evaporate again, and eventually be destroyed by sunlight. Its carbon may then become part of ethane or haze. A haze particle may settle for years, join a dune, travel in wind, enter an impact melt, and become altered by water. Titan's chemistry is a movement of matter through forms. The same carbon can pass from gas to liquid to solid. The same water can act as bedrock near the surface and liquid deep below. The same sunlight that dries weather also destroys the methane required for that weather. Titan survives through balances that are never permanent. This gives the moon a strange relationship with time. Its surface appears slow and cold, yet its atmosphere is chemically busy. Its landscape appears stable, yet rivers have cut canyons. Its seas look calm, yet their distribution changes with climate. Its methane cycle appears complete, yet methane is steadily lost. The world is active, but its activity is distributed across different clocks. Some changes occur in hours. Clouds rise. Some occur in seasons. Vortices move from pole to pole. Some occur in thousands of years. Shorelines migrate. Some occur in millions of years. Methane is transformed and landscapes erode. Some reach back to formation. The deep hydrosphere and atmosphere preserve the consequences of Titan's birth. Titan's history, therefore, becomes a journey through timescale. The 2-hour descent of Huygens revealed processes operating for billions of years. A 70-minute transmission from the surface changed planetary science. A 3-year Dragonfly mission will sample a world more than 4 billion years old. Brief measurements can reveal ancient systems when the right evidence is preserved. Huygens itself is now part of Titan's surface. The probe rests where it landed in 2005. Its batteries are silent. Its instruments no longer operate. Methane haze continues to settle around it. A rare storm may someday wet the ground again. Organic particles may slowly coat its exterior. The atmosphere that carried its parachute continues to move above it. No spacecraft can see the probe from orbit at useful resolution. It is a small human object in an immense landscape, a marker of one successful descent. Dragonfly will land far away. It will not visit Huygens, and it does not need to. The older probe established that landing was possible. It showed the texture of one site. Dragonfly will turn that single point into a traverse. When the rotorcraft prepares for its first flight, its rotors will accelerate in Titan's dense air. Dust or organic grains may move beneath it. The vehicle will rise. For the first time, A powered aircraft carrying a full scientific laboratory will fly across another planetary world. The scene may look calm. There will be no pilot visible, no sound transmitted live, and no immediate control from Earth. Commands will have been sent long before. The aircraft will navigate using its own systems. It will pass over dunes and bright ground, select a safe area, descend, and begin another period of measurement. Hours later, or perhaps on another communications cycle, the data will begin reaching Earth. The images will be old by the time anyone sees them because light itself needs more than an hour to cross the distance. Yet they will be new to humanity. The first close view of an untouched dune. The first airborne panorama beneath Titan's haze. The first drilled sample from a different world rich in atmospheric organics. The first local seismic record from Titan. Each result will arrive slowly. This pace suits the destination. Titan does not reveal itself in flashes. It was hidden for centuries by distance, then hidden by haze, then revealed by radar strip after radar strip. Its exploration has always required patience. The greatest questions may also require restraint. It would be easy to present Titan as a place on the edge of life. That phrase can suggest more than the evidence supports. Titan is unquestionably on the edge of our understanding of chemistry. Whether it is near biology is unknown. Its organic abundance may represent fertile prebiotic material, or it may show that organic richness can persist indefinitely without life. Its methane seas may permit unfamiliar self-organization, or they may be too cold and energy-poor. Its deep hydrosphere may contain warm, chemically concentrated liquid pockets, or the liquids may be isolated and short-lived within high-pressure ice. Every possibility remains constrained by physics. Titan does not allow imagination to replace evidence. It rewards imagination that produces testable questions. Could atmospheric products form increasingly complex molecules after contact with water? Dragonfly can sample impact-altered terrain. Are dunes made from haze aggregates, coated ice, or another material? Dragonfly can measure grains and composition. Does Titan contain a global ocean or a layered interior of ice, slush, and melt pockets? Seismic and tidal measurements can improve the model. Does methane weather occur at the landing region? Meteorological sensors can watch. Did internal material reach the surface? Geology and chemistry can search for signs. These are not abstract mysteries. They are questions attached to instruments that are being built. The distance between speculation and knowledge is sometimes one successful measurement. Cassini demonstrated this with the polar seas. Before radar images, oceans on Titan's surface were proposals. After repeated observations, liquid bodies became mapped geography. The same transformation may occur again. A debated chemical pathway may become measured. A suspected interior boundary may become constrained. A possible sedimentary process may become visible. Some ideas will fail. That is also progress. If no evidence of cryovolcanic material appears, models will change. If impact deposits show limited chemistry, expectations will narrow. If liquid water is distributed differently from current models, future mission concepts will adjust. Exploration does not promise the answer hoped for. It promises contact with reality. Titan is a particularly beautiful place for that contact because its surface repeatedly challenges familiar categories. It is a moon with an atmosphere more substantial than that of Mars. It is an icy body with deserts. It is a cold world with rain. It is a place with organic matter, but no known biology. It is a world whose visible seas are hydrocarbons, while its hidden water may exist as an ocean, slush, or isolated pockets. It is Earth-like in process and unlike Earth in material. The language used to describe it often has to borrow and then correct itself. Sand, but not quartz. Rock, but made from water ice. Rain, but methane. Seas, but hydrocarbons. Volcanoes, perhaps, but erupting cold fluids. habitability, but in more than one possible sense. These corrections are not limitations. They reveal how broad planetary nature can be. Earth provides one example of weather, geology, and chemistry. Titan shows that the underlying principles can be rearranged. A distant world does not need to resemble home in substance to produce familiar patterns. This recognition changes the way other worlds are studied. When a channel is found, the possible liquid must be considered rather than assumed. When haze is found, chemistry and hidden surfaces must be considered. When organic molecules are found, non-biological production must be examined. When a cold moon is found, internal heat and alternative liquids must not be ignored. Titan teaches scientific flexibility. It also teaches humility. For generations, astronomers could not see its surface and filled the gap with models. Some predicted a global ocean. Some imagined thick hydrocarbon layers. The real world contained seas, but mostly near the poles. It contained dry dunes across the equator. It contained a landscape more varied than any one prediction. The correct answer was not simply one of the old ideas. Nature combined elements in an unexpected geography. Dragonfly will likely repeat this lesson. The local surface may be rougher, softer, more layered, or more chemically varied than orbital data suggest. The first flight may cross features too small to exist on current maps. A sample may contain compounds no mission has previously measured on another world. The atmosphere may produce weather at an inconvenient or fortunate moment. Titan will not arrange itself around expectations. That is why going there matters. Remote observations can identify broad possibilities. Presence turns possibility into encounter. A drill touching the surface has a different authority from a spectrum taken across 1 billion kilometers. Both are necessary. Webb sees global atmospheric chemistry. Dragonfly will see local consequences. Cassini provides maps. Huygens provides one ground truth. Laboratories on Earth test reactions. Theory connects scales. Planetary knowledge is built from all of them. No single instrument tells the whole story. Titan's future investigation will remain collaborative across planets and decades. Scientists who worked on Voyager helped frame Cassini questions. Cassini researchers now support Dragonfly. Students who study Dragonfly data may design missions to the seas. The exploration of one moon can extend across several human generations. Titan's seasons reinforce that perspective. A researcher may spend an entire career observing one Titan year. A mission launched in one season arrives in another. A full climatic record demands continuity longer than most projects. The moon asks human science to think slowly. This is appropriate for a world whose rivers flow beneath a distant Sunday. Let the imagined journey move once more across its landscapes. Begin high above the atmosphere. Titan appears as a soft golden globe. The surface is invisible. A thin blue layer may outline the upper haze. Saturn occupies the distance, banded and ringed. Descending, the haze thickens. Light becomes diffuse. Winds carry the path sideways. Below the main layers, shapes emerge. Dark plains, bright uplands, channels, dunes. The surface approaches. Water ice cobbles rest beneath an orange sky. Far to the north, rivers enter methane seas. Far below, a water-rich hydrosphere of ice, slush, and perhaps scattered liquid pockets flexes under Saturn's gravity. Above, sunlight breaks methane into reactive fragments. Across the equator, wind arranges organic grains into lines extending beyond the horizon. At a crater, frozen deposits preserve a time when impact heat brought water and carbon chemistry together. At the poles, seasons move methane from air to ground and back again. Nothing in this system is isolated. The deep interior influences gases. The atmosphere builds sediment. Weather shapes geology. Geology stores chemistry. Orbital motion sets seasons. Sunlight drives reactions while slowly exhausting a crucial gas. Titan is a network of exchanges. Its appearance is quiet because the processes are slow. Its science is rich because the exchanges are many. There may come a day when Dragonfly's first results arrive. A new landscape will appear on screens across Earth. The image may show nothing dramatic by cinematic standards. A low ridge, dark grains, an orange horizon, perhaps a piece of pale ice. Yet every pixel will represent a place no eye has seen at that scale. The ordinary appearance of an alien ground can be more powerful than an imagined spectacle. It confirms that the world is not only a concept. It has texture, distance, weather, a horizon. For now, Titan continues without us. Clouds form when conditions allow. Methane falls. Channels wait. The northern seas remain beneath the haze. Dunes shift during rare strong winds. Organic particles settle. The deep hydrosphere flexes and dissipates tidal energy. Huygens rests silently. Dragonfly is being assembled and tested on Earth. The two worlds are separated by more than 1 billion kilometers, yet engineering and radio will connect them. A machine built in warm rooms under a blue sky will travel to a place where water is rock and methane is rain. It will carry instruments created from centuries of questions. It will fly because Titan's gravity is gentle and its atmosphere is deep. It will search not for a promised answer, but for evidence. And evidence, slowly gathered, will bring the hidden world closer. Titan began in human knowledge as a point beside a ringed planet. It became an atmosphere, then an orange veil, then a landscape of rivers and seas. Soon it will become a place crossed by flight. The methane rain may be rare. The rivers may remain dry for years. The seas may appear still. But the existence of the cycle has already changed the meaning of a habitable environment, a planetary surface, and even a river. Titan shows that nature can repeat a pattern without repeating a world. There can be rain without water. There can be rock made of ice. There can be seas beneath an orange sky. There can be complex organic chemistry without any known life. There can be a deep water-rich interior that refuses to fit neatly into the categories of ocean or solid ice. And there can be a distant moon that feels strangely familiar only until its materials are named. The familiarity draws us in. The differences teach us. The uncertainty keeps the journey open. For now, the haze continues to circle Titan. Methane continues to rise, condense, and return. The rivers continue their patient work whenever rain arrives. The dunes preserve the direction of ancient winds. The polar seas hold the dark reflection of a sun almost 10 times farther away than ours. Beneath them, water may persist in warm pockets and slow-moving slush throughout a hydrosphere hundreds of kilometers thick. A world of atmosphere, frozen water, hydrocarbons, and time waits beneath Saturn's rings. Good night.